Good evening, everyone. Good evening, everyone. Welcome to Goscore Learning. We are the fastest growing edtech industry in the Middle East, and our main aim is to provide quality education for all. We are here to make your learning easy. I am Dhanya Rakesh, teacher from the Department of Chemistry, Goscore Learning. Today, I am here with the first chapter of Grade 12 Chemistry, that is Solutions. The Solutions chapter, it's a very simple chapter. If you get the concept clear, you could easily score marks in this particular chapter. So, are you all ready? Can we start the session? Okay. So, first we can see what is actually meant by a solutions. In your lower classes, we have already discussed about that matter is divided into two types, pure substances and mixtures, right? These mixtures are further classified into homogeneous mixture as well as heterogeneous mixture. You have already learned the examples for this homogeneous as well as heterogeneous mixtures, isn't it? In that we have learned solution is a homogeneous mixture, whereas colloid, suspension, etc. are heterogeneous mixtures, right? So, what do you actually mean by a homogeneous mixture? Homogeneous mixture means in that the composition is distributed uniformly. If a particular mixture have a uniform composition, if the components are distributed uniformly, we will call it as a homogeneous mixture. And if the component is not distributed uniformly, it is a heterogeneous mixture. With one example, we can learn it easily. If we dissolve sugar in water, definitely we will get a uniform solution, right? That's an example for a homogeneous mixture. At the same time, if you dissolve sand in water, there the sand particles will settle down at the bottom and the water will be on the top layer. So we can say sand in water is a heterogeneous mixture. So why I discussed all these things is to explain what is actually a solution. Solution is a homogeneous mixture. See, a solution is a homogeneous mixture. That means it have a uniform distribution of its component. Okay. Homogeneous mixture of two or more substances whose concentration can be varied with certain limits. So what do you actually mean by this two or more substances? These substances are what we called the components of the solutions. And you already know that what are the components of the solutions? We can say it as solute as well as solvent, right? What is actually the solute? Like if you are dissolving sugar in water, we will take sugar less quantity, right? So the component which is present in lesser quantity is what actually the solute. Okay, that is the component which is present in less amount or less quantity in a solution is what we called as solute. Okay, and of course what will be the solvent? The component that is present in more amount or more quantity is what we call solvent. Okay, so in this particular chapter solutions, we are discussing about binary solution. What is the word binary means? Binary solutions means it have two components. So in this chapter, we are discussing only about the solutions which contain two components. Okay. So we are familiar with the solutions in that the solvent is usually water. So is there only liquid solutions available? No. There are gaseous solutions, solid solutions as well as liquid solutions. So which type is the solvent? What is the state of the solvent? That determines what is the solutions to be. Okay. So we can see different examples is for different types of solutions. That means first we will discuss about the gaseous solution. Okay. Gaseous solutions means there the solvent is gas. Okay. The solvent, see, this is the solute column, this is the solvent column. There are given some examples for solutions. Okay. So in that, for gaseous solutions, see, the solvent is gas. Okay. And the solute may be gas, liquid or solid. Okay. See the first example in that both the solute as well as the solvent is gas. In that case, we can say the example of mixture of oxygen and nitrogen. That means they're both the solute as well as the solvent is gaseous state. So that is an example for gaseous solution in which the solvent is a gas as well as the solute is also in the gaseous state. Okay. So the example for gaseous solution in which the solute and solvent is gas is the mixture of oxygen and nitrogen gas. Now let's see the example for gaseous solution in which the solute is a liquid one. See the example here. Here the chloroform is liquid that is mixed with the nitrogen gas where the nitrogen gas is the solvent. So the resultant solution is a gaseous solution. And the example for solid solute and gas solvent is camphor in nitrogen gas where nitrogen gas is the solvent and camphor which is in the solid state is the solute. So these all are different examples for gaseous solution in which the solute may be gas, liquid or solid but the solvent will be in gaseous state. That is why the resultant solution is a gaseous solution. Okay. Now let's see a liquid solution. Liquid solutions means the solvent will be in the liquid phase. Okay. So first example, see in three cases the solvent will be liquid state and here if you take a gas solute, that means if you are dissolving oxygen gas in water, the resultant solution will be a liquid solution in that the solute is a gas and solvent is a liquid state. Okay. And the second example is both are liquid. The solute and solvent both are liquids. That is the solution of ethanol in water. There we are adding the solute ethanol that is in the liquid state and the solvent we take it as water that's also in the liquid state. So there the solvent is in the liquid state. So the resultant solution will be liquid solution. Now this is a common example that we are seeing in our day-to-day life. That is the solid solute and liquid solvent. We can take any example like dissolving salt in water, sugar in water, glucose dissolves in water. These are the examples is for liquid solution in which the solute is a solid substance and the solvent is a liquid. Okay, that's all about the liquid solution. Now let's see solid solution. Solid solutions means there the solvent will be in the solid and we can dissolve the gas solute or liquid solute, solid solute. Whenever you dissolve a gas solute in the solid solvent, have the example of solution of hydrogen in palladium, where palladium is act as the solvent and hydrogen is the solute. So the resultant solution will be a solid solution. There palladium is the solid substances and hydrogen is the gas solute. Okay. And the next example is solid solvent and liquid solute. That means the amalgam of mercury with sodium. The last one is the solid solution, in which both the solute as well as the solvent is solid. That is, the example is the copper dissolves in gold, that we know, the 22 karat gold, that just to enable the strength of the gold, we are adding a small amount of copper. That is an example for solid solution. Okay, so these are the different types of solutions, and in which what is the solute and what is the solvent, and I have provided the examples for each type of solutions. I hope it's clear for you. Now let's see the different ways for expressing the concentration of solution. What do you actually mean by the concentration of a solution? Concentration means amount of the substance or the amount of solute that is present in the particular solution. So there are different ways for expressing the amount of the particular solute in the solution. Okay, see, these all things is the first four things is we have been learning from our lower grades, like the mass percentage, volume percentage, mass by volume percentage, parts per million. These things is we are already familiar, and the new things is are the molarity, molality as well as the mole fraction. Now let's see one by one in detail. The first one is the mass percentage. Mass percentage means the percentage weight by weight. That is the weight of the or the mass of the particular component of the solution divided by total mass of the solution. That means if you are saying 10 percentage weight by weight of a solution, that means in that the 10 gram of solute is made up into 100 gram of the solution. Okay, same way volume percentage means here we will be expressing the amount of the solute in terms of volume. So the volume percentage of the component, that is percentage V by V, the volume of the component divided by total volume of the solution. Like if it is a 10 percentage volume by volume solution, that means 10 ml of the solute is made up into 100 ml of the solution. Okay, and the next one is, the third one is the mass by volume percentage, that is the percentage weight by volume. We will express the mass of the particular component divided by total volume of the solution. This one we actually mainly we are using this mass by volume percentage in the medicinal preparations to express the concentration of the particular medicinal compound. Okay, so the next one is the parts per million, ppm. The parts per million, we usually use this way of expressing the concentration whenever there are trace amount of substance is present. Like if you want to express the impurities present in atmosphere or in water, we will use this parts per million. That is, when the solute is present in trace quantity, we will use the parts per million, and the parts per million is the number of parts of the component divided by total number of parts of all the components into 10 raised to 6. Okay, so mainly this parts per million is used to express the concentration of pollutants in water or atmosphere. This usually we are expressed in parts per million. Okay, these are all things we have already know, and we have been learning this from our lower grade itself. And the new way for expressing the concentration of a solution is the molarity. Okay, molarity usually we will express by the letter capital M. That means moles per liter or molar solution. Okay, capital M means that much molar solution. So what is actually this molarity? Molarity is the number of moles of the solute in 1 liter of the solution. See, this is the equation for finding out the molarity, where moles of solute divided by total volume of solution expressed in liter. So we can say molarity is the number of moles of solute present in 1 liter of the solution. Okay. So molarity, the number of moles of solute divided by volume of solution in liter. How we will find out the number of moles of solute? The number of moles of solute is given by the given mass divided by the molar mass of solute. Okay. So the number of moles of solute is given mass by molar mass. Okay. Or molecular mass of the particular solute. Okay. Now let's see the new term, that is molality. See, initially we have discussed about the molarity, that is expressed by capital letter M and is the number of moles of solute present in 1 liter of the solution. Here, molality we will be expressing with the small letter M. Okay, and is the number of moles of solute present in 1 kilogram of solvent. See, here the molality is the moles of solute divided by mass of the solvent in kilogram. Okay, in molarity we consider the total volume of solution. Volume of solution in liter, right? That is for the molarity. For molality, it is moles of solute divided by mass of solvent in kilogram. We will express the mass of the particular solvent in kilogram. That is the difference between molarity and molality. Okay. Now let's see the last way for expressing the concentration, that is the mole fraction. Mole fraction is nothing but the ratio of the number of moles of the particular component to the total number of moles of the solution. Like if we have two components like A and B, the mole fraction of the component, mole fraction we will be usually expressing with the letter chi. Okay, so for the mole fraction of particular component A, we can say it is chi A. It is the ratio of the mole fraction, number of moles of this particular component A, that is number of moles of A divided by the total number of moles, that is the number of moles of A plus number of moles of B. So, this is what the mole fraction of particular component A in the solution. That is the number of moles of the component divided by total number of moles of the solution. Okay. So, the mole fraction is the ratio of the number of moles of a particular component to the total number of moles of the solution, and this mole fraction is expressed with the symbol chi, and for particular component we can say the number of moles of the component divided by total number of moles of the solution. So, once we get the mole fraction of one component, it is not necessary to find out the number of moles of the second component by using the same equation. We can find out the mole fraction of the second component chi B by simply subtracting 1, the mole fraction of A from 1. That means the number of mole fraction of the second component is equal to 1 minus mole fraction of the first component. Okay. So, this is the very important equation that we have to find out the mole fraction of different solutions. Okay. Now, let's see some problems is based on this mole fraction, molarity and molality. The first one is a mixture contains 3.2 gram of methanol. Methanol means CH3OH. Methanol and 4.6 gram of ethanol, that is H5 OH. What we want to find out, find the mole fraction of each component. We want to find out the mole fraction of methanol as well as ethanol. Okay, so what it is given here, the mass of methanol and the mass of ethanol is given. We want to find out the molar masses of methanol as well as ethanol. Then only we can calculate the number of moles, isn't it? So first we can write down the equation for finding out the mole fraction. That is mole fraction of methanol. I'm representing with M. That is for methanol. Phi M is equal to number of moles of methanol divided by number of moles of methanol plus number of moles of ethanol, right? So, first we want to find out the number of moles of methanol. Number of moles of methanol is equal to given mass. What is the mass of methanol? It is 3.2. 3.2 divided by what is the molecular mass? It is CH3OH. So it will be carbon 12 into 1, that is 12. Hydrogen 1 into 3, that is 3. Oxygen 16 into 1, 16, and 1 hydrogen. So altogether it will come, it is 32 gram, right? So the number of moles of methanol is the given mass 3.2 divided by the molecular mass or molar mass 32 gram. So what will be the number of moles of methanol? 3.2 divided by 32, we will get the value 0.1, right? So same way we want to find out the number of moles of ethanol also, that I am representing with E, number of moles of ethanol. What is the given mass of ethanol here? It is 4.6. Now what we want to find out, the molar mass of ethanol, right? So what will be the molar mass of ethanol? It is C2H5OH. That means carbon 12 into 2, 24 plus hydrogen 5, oxygen 16, hydrogen 1. That is 46. That means 4.6 divided by 46. We will get the value 0.1. So, now we want to substitute these values here, right? So, the mole fraction of methanol is equal to number of moles of methanol. That is what we got here, 0.1, right? 0.1 divided by number of moles of methanol plus number of moles of ethanol. Number of moles of methanol is 0.1 plus number of moles of ethanol is 0.1. So what we will get? 0.1 divided by 0.2. That is 0.5. And note that there is no unit for the mole fraction, because in the numerator it is number of moles and the denominator also number of moles. So there is no unit for mole fraction. Okay. So here we got the number of moles of methanol. Now how we will find out the number of moles of ethanol? The mole fraction of ethanol. The mole fraction of ethanol is equal to 1 minus chi, or mole fraction of methanol, isn't it? So what we will get? 1 minus 0.5. That means 0.5. So what is the mole fraction of each component? The mole fraction of methanol is 0.5 and the mole fraction of ethanol is 0.5. Okay, I hope it is clear for you. Now let's see one more problem from the mole fraction. That is the mole fraction of 1.8 gram of glucose in 90 gram of water is. It's an MCQ based question. See, what we want to find out, the mole fraction of 1.8 gram of glucose that is dissolved in 90 gram of water. Okay, see, what is the formula for glucose? It is C6H12 O6. So what will be the molar mass? Carbon 12 into 6. Hydrogen 1 into 12, that is 12, and oxygen 16 into 6. 0, it is 180, right? So how we will find out the mole fraction of glucose? Mole fraction of glucose, that is chi. Glucose is equal to number of moles of glucose divided by number of moles of glucose plus number of moles of water. Isn't it? The number of moles of glucose, what it will be? It will be number of moles of glucose is equal to 1.8. Given mass 1.8 divided by 180, that is 0.01. Isn't it? So, what will be the number of moles of water? Here the given mass is 90 gram. 90 divided by molar mass of water is 18. We will get the value 5. So, by substituting this value 0.01 divided by 0.01, 0.01 plus 5. So here approximately it's an MCQ based question. So we can approximately do the calculation as 0.01 divided by 5. We will get the value 0.0019. Okay. So since it is an MCQ question, by doing this we can easily find out the answer. Okay. So I hope this is clear. The mole fraction of 1.8 gram of glucose in 90 gram of water. The mass of water it is given and the water molar mass we know. So we can calculate the number of moles and the glucose mass is provided and the molar mass of glucose that we can calculate by substituting, simply by substituting that in the equation, we can easily find out the mole fraction of glucose. Okay. Now see one more question, that is a 5.2 molar aqueous solution of methyl alcohol is supplied. Okay, what is the mole fraction of methyl alcohol in the solution? Okay, so here what it is given, 5.2 molar. 5.2 molar means we have expressed the concentration in terms of molality. So what is molality? Molality is the number of moles of solute divided by molality. That is the denominator is mass of solvent in kilogram. Isn't it? So that is what the molality, small letter m. So here it is given that the solution is 5.2 molar. That means it contains 5.2 moles of solute in 1 kilogram of solvent. Isn't it? So that one we can write it as 5.2 moles of solute in 1000 gram of solvent. Isn't it? So what we actually want to find out, the mole fraction of methyl alcohol. The mole fraction of methyl alcohol, it is given as high methyl alcohol, or we can write it as the methanol. See, chi is equal to number of moles of methyl alcohol divided by number of moles of methyl alcohol plus what is it's given? It's an aqueous solution. That means one component is methyl alcohol and the second component is, since it's an aqueous solution, the second component is water. So here the number of moles of water. Okay. So the number of moles of solute, it's already provided in the question. That is, the number of moles of solute is 5.2 molar. So that means the solution contains 5.2 moles of methyl alcohol. So the number of moles of methyl alcohol it's given. So now what we want to find out? The number of moles of water. Isn't it? So for the number of moles of water, what is the mass of water? It is, we are taking 1000 gram of solvent, isn't it? So the mass of water is 1000. That 1000 divided by what is the molar mass of water? It is 18, isn't it? H2O, oxygen 16 plus 2 hydrogen, it is 18. So 1000 by 18, we will get the value 55.5. So simply by substituting here, what we will get? 5.2 divided by 5.2 plus 55.5, that means 5.2 divided by 60.7. Okay, by doing this calculation we will get the value 0.085. That much is the number of mole fraction of methanol in the 5.2 molar aqueous solution of methanol. Okay. So whenever the question is provided like this, if it is molar, if it is a molarity, the question will be given as 5.2 molar. That means it is expressed in molarity. Okay. So if it is given 5.2 molar means it's given in terms of molality. That is the number of moles of solute divided by mass of the solvent in kilogram. So from that we will get the mass of the water or any solvent that we are using in that particular solution. Based on that we can easily substitute the values in the equation and we could find out the solution. Okay. Now we have done for the mole fractions only. Now let's see one question based on the molarity as well as molality. So find the molarity and molality of a 15% solution of H2SO4 and the density of H2SO4, it's given in the question 1.020 gram per centimeter cube. Now see how we will find out the molarity as well as the molality. Okay. So here what it is given? 15% solution. What do you mean by 15% solution? 15% means we have dissolved 15 gram of H2SO4 in 100 gram of the solution. Isn't it? That is what the 15% solution means. So here first we can find out the molality. Molality, it is the number of moles of solute divided by mass of solvent in kilogram, right? So the molality, how first we want to find out the number of moles, right? So what is the number of moles of water, H2SO4? Number of moles is equal to given mass. Given mass is 15 gram, right? So 15 divided by, what is the molar mass of H2SO4? Hydrogen it is 2, sulfur 32 and oxygen 16 into 4. That is 64, right? So we will get 100. Okay, we will get 100 gram as the molar mass. So 15 divided by So let me check. So for 32, 2. So, okay. The number of moles we get it as 0.15. Okay. So, now what we want to find out? The molality. Okay. So, the molality is the number of moles divided by total mass of solvent in kilogram. So, how we will get the mass of the solvent? So, here we have taken the 100 gram of solution and in that we added 15 gram of the solute. So, we get the value of solution. We know the amount of solution and also the solute, right? So, how we can find out the solvent? Just simply by subtracting them from 100 to 15, we will get the mass of the solvent, isn't it? So, the mass of solvent is equal to 100 minus 15. That means it is 85 gram. So, for molality, we want the solvent, mass of solvent in kilogram. So, it will be just simply dividing by 1000, you will get the mass in kilogram 0.085 kg. So, simply substituting these values, the number of moles, it is 0.15 divided by the mass of the solvent, that is 0.085. 0.085, you will get the molality of the solution, and by doing the calculation, we will get the value as 0.153. That much molal it is, or either you can express the moles per kilogram or molal. Okay. Now, how we will find out the molarity? Molarity is nothing but the number of moles divided by total volume of solution. So, for the total volume of solution, how we could find out? Because the density it is provided here and we know the mass of the solution. So, we can easily find out the volume of solution, isn't it? So, for volume of solutions, how we can find out? The volume of solution is equal to density is equal to mass by volume. So, from that, we can find out the volume as mass by density, isn't it? So, the mass by density we will get simply substituting mass 100 gram and density it is given 1.020. We will get the volume of the solution. Substitute the value in this, that is 0.15, and the value that we are getting divided by 100 by 1.020, that is 98.04. We can easily find out the molarity of the particular solution. Okay, that is the way we can find out the molarity and molality. See, if you know the concept clear, if you are aware about the equations, simply by the logic we can easily substitute the values and we will get the answer and can score good. Okay, so that are the different examples for problems related to the different methods for expressing different ways of expressing the concentration of a solution. That we have discussed the mass percentage, volume percentage, mass by volume percentage, parts per million, molarity, molality, as well as the mole fraction. Okay, I hope it's all clear for everyone. Now, we can discuss about the term solubility. Okay, so what do you actually mean by solubility? If you take 100 gram of the solvent and you add 1 gram of the solute, you could easily dissolve it, right? Then you add 2 gram of the solute, that also you can dissolve. If you add 3 or 4, after adding 10 gram of the solvent, you dissolve it properly, and after that if you couldn't add more solute to that solution, that is what we called the solubility. That means the maximum amount of the solute that can be dissolved in a 100 gram of solvent at a given temperature. Okay, so solubility is nothing but the maximum amount or maximum number of solute particle that we can dissolve in 100 gram of the solvent at a given temperature. Okay, so I hope solubility is clear for you. Now see the solubility of gas in liquid. Okay, see, we can express what is the solubility of gas in liquid and what are the factors that affect the solubility of gas in liquid. Okay, so solubility of gas in liquid means we are dissolving gaseous thing in a liquid solvent, right? So there the main two factors are pressure and temperature. Okay, first we can see the pressure. The effect of pressure on the solubility of gas in liquid is expressed by a very important law, that is the Henry's law. Okay, so according to Henry's law, the solubility of a gas in a liquid is directly proportional to pressure exerted by the gas. So the solubility of a gas in a liquid is directly proportional to the pressure of the gas. So, according to this, see, according to Henry's law, we can say that the pressure of the gas is directly proportional to solubility. Solubility means the concentration, right? So, we can say the pressure is directly proportional to mole fraction. Okay, that is the solubility of gas. We are expressed in mole fraction. So we can say the pressure is directly proportional to mole fraction. So when you change the proportionality constant, we can say P is equal to KH into phi. Okay, so here the constant KH is the Henry's constant and P is the pressure of the gas and chi is the solubility of gas. See, so what we can say, this Henry's constant is equal to pressure divided by chi. That is pressure divided by the solubility of gas. So from that we can say that Henry's constant is inversely proportional to mole fraction chi. So what it is, whenever the value of this Henry's constant is high, the solubility of the gas in liquid is low. Okay, so this Henry's law constant is inversely proportional to the solubility of gas, and this Henry's law is very important, that the solubility of a gas is directly proportional to the pressure of the gas. Okay, now see some applications of this Henry's law. That's also very important in this section, that is the applications of Henry's law. The first application is, this Henry's law is applicable in the carbonated drinks. You all are familiar with the carbonated drinks, right? So in that, the gas is solubilized the gas is dissolved in the particular solvent under high pressure, and it is based on the Henry's law. So whenever the pressure increases, the solubility of gas increases, right? So the first application is the production of carbonated drinks. And the second main application is in deep sea diving, that is scuba divers. So in the deep sea, there the pressure is more, isn't it? So there the solubility of gas will be high. So there more amount of oxygen and nitrogen will be getting into the blood, and the solubility also increases, isn't it? That is under the sea. So when the scuba divers comes on the top of the water, there the pressure got decreased. So what will happen? The solubility decreases and this dissolved nitrogen will get out from the blood, and This nitrogen will cause the blockade in the capillaries. That condition is what we call bends. This is very painful condition and it is very toxic also. So, to avoid this bends, the as well as the toxic effect of high amount of this nitrogen concentration in the blood, the scuba divers use the air-filled tanks that is filled with diluted helium, that is 11.7 percentage of helium, 56.2 percentage of nitrogen and 32.1 percentage of oxygen in it. Okay, so by this, we can reduce the more concentration of nitrogen in the blood. So, here in the scuba diving, why these bends are occurring? It's because at the deep of the sea, the pressure is more. That means the amount or the solubility of the gas increases there. So, more amount of gases will be getting dissolved in the blood, and when they reach on the top of the water layer, there the pressure is less, so the solubility decreases. So pressure is directly proportional to solubility, right? So there the pressure is less and the solubility of gas get decreased. So there this dissolved nitrogen will come out and it will cause the blockade of the capillaries. There that bends or the scuba diving filling air cavities, that all are based on the Henry's law. That is the pressure directly proportional to solubility. So I think this is clear for you. That is in the deep sea diving or scuba divers to avoid the bends or compression sickness. Okay. The next thing is for climbers or people who live in the high altitude. That is at the high altitudes, the pressure of oxygen gas is less. So what will happen? As the pressure decreases, the solubility also decreases, right? So the amount of oxygen in the blood will be very less. Okay, so at high altitudes or for the mountain climbers at the top of the altitudes, there the partial pressure of oxygen is very less, that the solubility of oxygen will be very low for them. So that condition is what we called anoxia. Okay, there also we can apply the Henry's law. So where as the pressure decreases, the solubility of gas decreases. So these are the main applications of Henry's law, and according to Henry's law, the solubility of gas is directly proportional to the pressure of the gas. Okay, and there we have mentioned the Henry's constant, and this Henry's constant is inversely proportional to the solubility of gas. And we have discussed about the applications of Henry's law, that is mainly in the carbonated rings and in the scuba divers, as well as the mountain climbers or the people who live in the high altitudes. Okay, now let's see one problem based on this Henry's law. That is, the value of Henry's law constant, the KH values of helium, hydrogen and oxygen are respectively given in the question, and we want to find out the order of the solubility. Okay, so here what it actually happens is, see, we have provided with the KH values of helium, hydrogen and oxygen, right? So for helium, it is 144.97, and for hydrogen, it is 69.16, and for oxygen, it is 34.86. So what we discussed in the Henry's law, as per Henry's law, the KH is inversely proportional to mole fraction or the solubility of gas. So as the KH value increases means the solubility decreases. So what it is? Since the KH value for helium is more here, so it will have a very low solubility. So helium will have the solubility lesser than that of hydrogen, which is lesser than that of oxygen, right? So which option is correct here? Helium lesser than hydrogen, which is lesser than oxygen. So this is the applications is of Henry's law and the problem based on Henry's law. So I hope this Henry's law is clear for you. And we have discussed one more thing, that is the temperature. So now let's see the temperature, how the temperature will affect the solubility of gas in liquid. We all know that we will use it to store the carbonated drinks in the refrigerator, right? So that means the solubility of gas increases when the temperature decreases, isn't it? So the solubility is inversely proportional to temperature. As the temperature increases, the solubility of gas decreases, and as the temperature decreases, the solubility of gas increases. That's why we used it to store the carbonated drinks in the refrigerator. So, I hope the effect factors that affect the solubility of gas in liquid, that is the pressure as well as the temperature. The pressure we have expressed by using the Henry's law, and the temperature, it is inversely proportional to solubility of gas. So in this session we have discussed about the solutions, different ways of expressing the solutions and about the solubility and solubility of gas in liquid. Okay, and we have did the problems related to these particular portions also. I hope it's all clear for you. And your Satin sir will be coming with the second part of your applications of derivatives chapter on the coming Wednesday, that is on the 18th October. So stay tuned with us. I will be coming with the second part of this solution chapter soon. Thank you for watching us.